Okay, hello, and welcome to the Homework Help live stream. I'm going to go ahead and get my posts made to let the world know, and by the world, I mean whoever might see it that follows me on Facebook and Instagram. Okay, we got that up. Let's share that to our story. That is up. Let's check that it worked here too. Excellent. Okay, so here, the Homework Help live stream. If you have homework problems that you need help with in math or physics or maybe even other subjects, then you can ask them here in the chat, and I will do my best to help you solve it live. In the meantime, I'm just going to be working on my own math and physics problems that I have to pass the time. Let me just pull this up in a different tab and see how it sounds. Do we have sound coming through? We do. Excellent. Okay, let's see here. I'm going to start with some geometry. So we have angle, this one, 75 degrees. And this one is 105 degrees. And we need to fill in all of the other angles. So let's start with this one. So if we say this is like some angle A, then we can say 75 plus A has to equal, well, if we're going across a straight line, that is to be 180 degrees. So we can subtract 75 from both sides. Not 5, 75. And say that A is equal to, that would be 105 degrees. Guess I should also mark on this picture that these are parallel and these are parallel. That makes this 105. Then, by that same logic, if we look at this angle, maybe we say that's B, then 105 plus B has to be 180. But we already know that 105 plus 70, or 180 is 105 plus 75. So this side has to be 75 degrees. And then if we do that same argument again, find that this angle is 105. Now, because this line is parallel to this line, we can say that this angle is actually the same as this angle, making this one 75 degrees. And from there, we end up with all these other angles being the same too, because 75 plus this angle has to be 180, which means this is also 105. And 75, 105. And then we can see both of these other intersections are going to be exactly the same. Which is great and convenient when you're trying to fill in this whole thing. Okay, next let's do an algebra story problem. So, total investment, $10,000. We're going to look at investing some money. We'll say we invest some of it in Fund A. It had a 6% profit. And Fund B had a 2% profit. And the total profit received is $374. So now our question is, how much did we invest in Fund A and in Fund B? So let's set up some equations. Let's set up one equation for the amount invested and one for the profit earned. So for the amount that we invested, we can just say that however much we invested in A plus however much we invested in B is equal to 10,000, since that is the full amount of money that we invested. A plus B equals 10,000. Now for the profit that we earned. Let's think about each of these individually. So Fund A earned a 6% profit. That means that however much we put in Fund A, that amount became itself plus 6% of itself. So in A, we ended up with the small letter A, the amount we invested in it, plus 6% of A, or 0.06 times A. And if we combine those, it's going to be 1.06 times A. So 1.06A is the amount of profit that we earned off of our investment in Fund A. And then it'll be similar for B. we earned 2% back on B. So the amount we invested there became itself plus 2% of itself, or 0.02B. And if we put those together, that's 1.02B. So that is the amount of profit that we made off of our investment in B. Or rather, these are not the amount that we made off of it, but the total amount that it became at the end. So the total amount of money that we have at the end is the 10,000 plus 374. That's how much these two investments are worth now. So let's write these. Let's give these numbers. Let's subtract equation. Let's take equation 2 minus equation 1 and see what we get. So 1.06a minus a would be 0.06a. 1.02b minus b would be 0.02b. And 10,374 minus 10,000 would just be 374. So let's see, what do we do now? I'm going to turn these into fractions. So this is really divided by 100 and times 6. So 6 divided by 100a. That's how the 6% is a fraction. 6 out of 100 plus 2 out of 100b equals 374. Then we can multiply both sides by 100. And we'll cancel out these denominators. So we'll have 6a plus 2b is equal to 37400. And we need to move somewhere else on the board because we are running out of room. I'm going to go ahead and rewrite equation 1 up here at the top. A plus b equals 10,000. Okay, 6a plus 2b is 37,400. Also from equation A, let's go ahead and solve for b. So b is equal to 10,000 minus a. Let's take that and put it into this equation 2 that we have. Bring that up here. We have 6a plus 2 times. I'm going to put a big parentheses where b is, since we know what b is equal to. 10,000 minus a, and that's still equal to 37,400. So let's distribute this. 2 times 10,000 is 20,000. Minus 2a equals 37400. Now let's subtract 20,000 from both sides. We'll get rid of that on the left-hand side. So over here, 37,400 minus 20,000 is going to be 17,400. Then on the left-hand side, all we'll have left is 6a minus 2a. 6 minus 2 will give us 4a. So then a will be equal to, let's see, can we do that without a calculator? Obviously the 400 divided by 4 will be 100. What's 1,000 divided by 4 is 250. So 250 times 17, we would get 2,500 plus 17 times 250, or plus 7 times 250. Okay, you know what? We'll just use a calculator instead of trying to carry all those numbers in our head. And we get $43.50. So the amount we invested in A is $4,350. And then that means, now that we have A, we can come up here and calculate B. B is $10,000 minus that. And that should be 5,700 something. Nope. 5,600 something. 5,650. So we invested $43.50 in Fund A, and we got back a 6% profit on that. So 6% of this was added on to our total amount of money that was in this investment. We invested $56.50 in Fund B, and 2% of that was added on to 2% of $56.50 was added on to the total amount of money in that investment. And so altogether, that ended us up with $10,000 plus $374. Okay. Now I actually forgot to stock up on problems to solve again. So let's look around for some. Okay, I found a bunch of integrals. Those are my favorite. So let's work on those. Start with our I equals. Now let's actually pick some out. So this is where we really go off the script because I have no idea if I can solve any of these. Okay, here's what we'll try. The integral of x squared over 25 over the square root of 25 plus x squared dx. So this is screaming trig substitution to me. So let's think about what kind of trig substitution we could do. So let's remember our identity. Sine squared of theta plus cosine squared of theta is equal to 1. And we want to get 1 plus a trig function to match this form. Well, we can't really get 1 plus a trig function here because we would have to subtract these to the other side, so it would always be negative. So let's try to look at the tangent and secant form. Let's divide everything here by cosine squared. So sine over cosine is tangent. That gets us tangent squared of theta plus anything divided by itself is 1, and 1 over cosine is secant. We get secant squared theta. And what do you know? We have 1 plus a trig function. So we're going to end up letting x equal something times the tangent of theta. So why don't we let x equal 5 times the tangent of theta. Then that tells us that the derivative of x with respect to theta, oh, my marker's going, is d theta of 5 tangent theta. The 5 will just come through our derivative, and the derivative of tangent is secant squared. Then we'll bring the d theta to the other side and bring the 5 over here. So this is all well and good, but we don't seem to have a secant squared of theta. Oh, wait a second. We don't need a secant squared of theta to absorb into the dx. Do we? Bring that 5 back over. Dx simply equals that stuff. What happens with our x squared, though? This also means that x squared equals 5 squared times tangent squared of theta. Yeah, that should be fine. So all of this together means that our integral now equals, we're going to have 5 squared plus 5 squared tangent squared of theta. X squared is 5 squared tangent squared of theta. And we have a 5 secant squared of theta d theta. Let's simplify this radical. So 5 squared plus 5 squared tangent squared. Why don't we factor out that 5 squared from both of them, from both terms, to get 1 plus tangent squared. We have something squared inside a square root, so we can just bring it outside. And remember from up here, 1 plus tangent squared is actually just secant squared of theta. And look at that, something squared inside a square root. So that becomes 5 times the secant of theta. So when we rewrite our integral on the next line, let's bring out all of these 5's. We have 5 cubed on top and a single 5 on the bottom times the integral of tangent squared secant squared over secant. Now we definitely need to erase some stuff. We are probably going to have to erase most of the board a few times. So secant squared divided by secant is just secant to the first power on top. It's not even a fraction in there anymore. This 5 cubed divided by 5 just becomes a 5 squared. And now, what do we do here? We could break down, maybe. I'm not sure if it would help if we say that tangent squared theta secant theta is actually sine squared over cosine squared, another cosine on the bottom. Would that do anything for us? We could do another substitution and say something equals cosine, and then we would have a sine on top. I don't think that would really work. Because if we did something like letting u equal cosine, then du would be negative sine but not sine squared. What if u was cosine squared? No, what if u was cosine cubed? Then we would get 3 cosine squared. Oh yeah, we would still have the cosine squared in it. So I don't think that's really going to help us. What if we say tangent squared is nothing but secant squared minus 1 times secant, or secant cubed minus secant, I think we can integrate the secant part by itself for sure. In fact, I'm sure that both of these are tabulated integrals that you can find in the back of a textbook. In fact, I'm going to check that right now in my Rogowski calculus book. Yep, there is a formula for secant cubed, and secant we'll just do by hand. So that is where we're going to take it. I'm going to go ahead and actually move some of this farther up. So we'll say that after all of this stuff, the integral is 5 squared tangent, no. Secant cubed minus secant. And let's remember that our substitution was x equals 5 times the tangent of theta, because we will probably need to undo that later. Yeah. So let's say that this is equal to negative well, no. Let's say it's 5 squared times the integral of secant cubed minus 5 squared the integral of secant. Now for secant, let's actually rewrite that. So the integral of secant theta is equal to the integral of d theta over cosine of theta. Oh, maybe I was thinking of doing tangent by hand instead of secant. I know I've done tangent by hand. Is secant another one that's in the tables? I feel like it should be. Okay, yeah, it is. Oh, yeah, of course. That's natural log of secant plus tangent. Oh, wait, yeah, I think we can do that. Yeah. So the integral of secant is the integral of 1 over cosine, but we can do a trick here. We multiply by something. Oh, it's been forever since I've done this. Is it multiplying by sine over sine? What would that get us? We would have tangent divided by sine. No, I don't think that's it. Somehow we should end up with... Okay, well, I'm not going to spend too much time on that since I don't remember how to do it by hand. But it can be done. So this is 5 squared. From our table, the integral of secant cubed is a half secant tangent plus a half the natural log of secant tangent. Nope, not secant times tangent, secant plus tangent minus 5 squared times the... Whoop, I lost it. Where'd it go? There it is. Natural log of secant plus tangent. And since we just evaluated an indefinite integral, we'll get a plus c at the end. So we actually have the same natural log in both terms, so we can combine those. They're both times 5 squared. We have a -1 and a plus a half, so it would become minus a half. So I'll just change that to minus a half, put the plus c up here, and we'll erase this line. Okay, now comes the fun part. So we know from this equality that tangent of theta equals x over 5. So everywhere we see tangent, we can just go ahead and plug that in. As for secant, though, we need to draw a triangle. Actually, I should give myself more room with that triangle. Let's do it over here. So let's say theta is up here at the top. Tangent is opposite over adjacent. So that means x is on the opposite side of theta and 5 is on the adjacent side. Then the hypotenuse is x squared plus 5 squared. The exact same radical that we had in our original integral, and that is not by accident. So the secant of theta is 1 over the cosine, which would be if, let's see, so TOA, cosine is adjacent over hypotenuse, so this would be hypotenuse over adjacent. So secant is the square root of x squared plus 25 over 5. So everywhere we have secant, we will plug that in. And this is just going to be a grand old time. Okay. I'm going to try to not erase that so I don't forget what it's supposed to be. This will be 5 squared over 2 times the secant times the tangent, that's x over 5, minus 5 squared over 2 times the natural log of the absolute value of, hey, it's right there where I need it, plus x over 5 plus c. And we can do a little simplification. There's 2 5s on bottom and 1 on top. Those all cancel out. These both have a 5. We could factor that out to have 1/5 times that stuff, but I don't think that helps us. Natural log of a product, we could split into natural log of 1/5 plus natural log of this stuff, but that would just be messy, and we'd have to write an extra term on the outside that we don't really want. So I think really the most that we'll be able to simplify this is a half. Actually, let's say it's x over 2 times the square root of x squared plus 25 minus 25 over 2 times the natural log of, just because I'm pressed for vertical space, I'll go ahead and say it's a 1/5 times the square root of x squared plus 25 plus x plus c. And there is the final answer, about a mile wide. That was fun. I actually did have fun with that. It would have been a lot more fun to do the integral of secant by hand. But actually, now that I'm thinking about it, I think I remember that being a very long integral with a lot of not obvious tricks. It was not something quick and easy. So actually, it's probably good that we didn't do that. Okay. Let's see another one I'd like to try. I think I have an idea of the trick we can use for it. Start with our integral equals integral of secant over tangent. So I think what we can do here, we'll want to end up at the end doing a substitution where we let u equal tangent, and then we get a secant squared in our du that will absorb something else. But we do need to do one algebra trick. We're going to multiply by 1, and in this case our 1 will be secant over secant. Maybe. Actually, now I'm not so sure that it will work now that I'm seeing it. What if we did tangent over tangent? Well, that... okay. Okay. Yeah. So, this is tangent squared with secant tangent on top. Now, remember, since tangent squared plus 1 is secant squared, so this is actually secant squared minus 1 on the bottom. Now we're going to let u equal secant of theta. And that means that du d theta is secant times tangent. Then we'll bring the d theta over. And look at that, that's our numerator. So that means our integral is now du over u squared minus 1. Maybe not the best, but it's certainly a big transformation. How can we do this now? U squared minus 1. We can't do another sub and say something equals u squared because we don't have a u on top. But I think we can say this is u plus 1 times u minus 1. We get u squared, we get negative 1, and we get a plus u and a minus u that cancel out. So this this is actually, I guess, going to be a partial fraction decomposition, which is not where I expected this to go. Let me copy some of this down, and then we'll start working on that while I erase the rest of it. And we'll copy down our substitution that we made. Yes, Bestowal Pants, you may ask a question. Go for it. While you are... Oh, okay. While you're doing that, I'm just going to go back to my calculus textbook and remember how to do partial fraction decomposition, because I've tried to do that as infrequently as possible ever since I took Calc 2, because that was my least favorite one. Okay. Right, so we say this fraction with the product on the bottom is equal to a sum of fractions with those two factors and an unknown coefficient on the top. Then we have to solve it out. Okay, that shouldn't be too bad. Okay, that was a really quick partial fractions. Okay, capacitor problem. Okay, let's see if we can work that out. I'm gonna go ahead and just get rid of all this. I don't think we'll have time to get back to it before the end of the stream. So we have a capacitor, parallel plate capacitor, and the distance is changing. Initially it has capacitance is 5 microfarads and Q equals 3.2 millicoulombs. It's initial. The final capacitance is 1.5 microfarads. Okay. How much work is done by the force that changes it? So we'll need to look at our formula for the capacitance. That is C equals epsilon naught times A over D, if I remember correctly. I'll need to double check that. And if we have a change in this, then it would be based on a change in D. And that force is going to be applied over this change in distance. So the work will be equal to the force times the change in D. So let me double check that capacitance formula before we move on too far ahead of that. Okay, yeah, it's just epsilon naught A over D. And we also have the charge, so would probably be remiss not to use that somehow. let's solve this for the change in D. So that would be epsilon naught A over delta C. So we could plug that into here. The question is, what is that force? Also, what are we going to do about this area term? Let's go ahead and rewrite this up at the top and then give ourselves more space to work. So F times epsilon naught A over delta C. So we don't have any information about the magnitude of the force or the time that it's happening. Let's see. What else can we write down that we know? We know Q equals C times the potential difference across the capacitor. So if the distance is increasing, but the charge and the area are staying the same, we would have to expect the voltage to decrease. How does that help us work back to here, though? We could say maybe A is Q D over epsilon naught delta V. But that doesn't really help us with okay, maybe I need to untangle some of what we wrote up here. An energy problem. Yeah. So the potential energy in a capacitor should be 1/2. It's either C delta V squared or maybe Q delta V squared. Yeah, that makes a lot of sense. That would make it a lot easier. Capacitor energy 1/2 QV. No, CV squared. Okay. Yeah, that's probably where we're supposed to go. So then we don't need to worry about work being force times a distance. We're going to say that work is equal to the change in this potential energy. So let's look at that. So delta U would be final minus initial 1/2 C final delta V final squared minus 1/2 C initial delta V initial squared. So 1/2 let's see. So for each of these, if we know Q equals C delta V, Q equals C delta V, then delta V equals Q over C, and delta V squared equals Q over C squared. So this is 1/2 C final Q squared over C final squared minus 1/2 C initial Q squared over C initial squared. So let's factor out that Q squared over 2. Then we'll have 1 over the final capacitance minus 1 over the initial capacitance. And then that's all numbers that we know. So let's bust out our calculators. So this is our final line. We'll say the work is equal to 3.2 squared times 10 to the minus third, also squared, divided by 2. The final capacitance is 1.5 on the bottom. 10 to the negative 6 on the bottom would be 10 to the positive 6 on top. Minus 5 on the bottom, 10 to the 6th on top. So we get 3.2 squared over 2 times 1 over 1.5 minus 1/5. Bring out the 10 to the 6th. 10 to the minus 3 squared is a 10 to the minus 6. So actually all those scientific notation bits are going to cancel out. So let's see, 3.2 squared, divide that by 2, take 1 divided by 1.5, that's 1 over 3/2, so that's 2/3 minus 1/5. We'll take that times the other part, and that should be 2.389. And if we did this all in SI units, which I think we did, that would be joules of work done to the capacitor. Okay, let me look over that and see if that seems right. So we are cutting the capacitance by more than half, and if it's proportional to 1 over the change in D, then we would expect it to be expanding by more than half, except we don't really have any information about how much it's expanding. But I think this should all work, because to be able to change the potential energy inside the capacitor, if the charge stays the same, then you have to change the voltage, and we can substitute in for that voltage with our relationship Q equals C delta V for both parts. And then, yeah, it's just numbers that we know. So you might want to double check my actual calculator stuff and my simplification that I did, because I go a little wild with the powers of 10, trying to simplify those out to the side. But I think at least up to here, that should all be solid. So I hope that has helped you, Bestowal Pants. It is actually time to end the stream for tonight. So thank you for tuning in. You are my very first viewer that has asked a homework question. So I'm very glad I was able to help you out with this one. And I hope I'll see you again. We'll be doing another homework live stream Tuesday and Thursday of next week. You can check my Facebook and Instagram pages for information on when those are posted. I believe there are links to those here on my channel. Yes, if you go to the About page on my channel, you can find a link to the Facebook and Instagram. And so I'll be posting when the next homework live streams go up. So, until next time, have a radical day.